So this video will wrap up carboxylic acid derivatives. So as a reminder, we've been focusing on 4 such derivatives. The acid halide, in particular, we've really focused on the acid chloride, the acid anhydride, which has the oxygen connecting 2 carbonyls, the ester group, and the amide. And then also we mentioned that a nitrile is also a carboxylic acid derivative. Recall this is the order of reactivity with our acid chlorides at the top and our amides being the least reactive. And it's easy to go from a more reactive to a less reactive derivative, but very difficult to go from a less reactive to a more reactive. This is the overview of the reactions I've discussed of acid chlorides and an overview of the reactions of acid anhydrides. And notice the similarities between the reactions you can do with anhydrides and the reactions you can do with chlorides. So we're going to finish up with esters and amides. Esters can be prepared by SN2 reaction of a carboxylate with an alkyl halide. So to do this, you start with a carboxylic acid, you add a strong base like hydroxide, which is going to deprotonate the hydrogen there, and then you do an SN2 reaction with an alkyl halide depending on what group you want to add on to that oxygen. There's also an acidic way of doing this called Fischer esterification, and with this you take a carboxylic acid and an alcohol in the presence of acid, and the group from the alcohol, so the OR group, becomes your OR group of your ester. Here is the mechanism. Notice that there are lots of proton transfers in this mechanism. 1, 2, 3, 4 proton transfer steps, a nucleophilic attack step, and a loss of a leaving group step. And since this is an acid, this is going to have our first step be a proton transfer to the carbonyl oxygen, and then that's followed by nucleophilic attack. Then we have a series of proton transfers that get us to this intermediate where we can finally kick off water as the leaving group, and then a final proton transfer gets us to our ester. So notice here that the OMe of the ester comes from the alcohol. And here we have an animation of the Fischer esterification. So first we're protonating the carbonyl oxygen. Now our alcohol is going to come in and do a nucleophilic attack, so it's going to form a bond with the carbonyl carbon, breaking the pi bond simultaneously. Then we're going to do some proton transfers. And now we are ready to lose water as a leaving group. So there water leaves, there's water leaving. And then the final step would be one more proton transfer to get to our ester product. The mechanism for the Fischer esterification has been experimentally supported through an isotope labeling experiment where they used an isotopically labeled oxygen atom to prove that the oxygen of the ester here came from the oxygen of the alcohol. So this oxygen in the starting acid goes away in the form of water, and the new oxygen comes from the alcohol. And this process is equilibrating, meaning it goes backwards and forwards, but you can push the product formation by removing water from the mixture. You can also make esters by reacting alcohols with acid chlorides. That's a reaction that we've already seen. Esters can undergo hydrolysis under basic conditions, which we use the word saponification for that. So with this, we use hydroxide, a strong base, and then we have to do an acidic workup. So if you look back to the acid chloride hydrolysis with strong base, you'll see it's identical to this, where the hydroxide is going to attack the carbonyl carbon. We get to this intermediate. The O- donates its electrons to reform the carbonyl, kicking off OR. And then we have a carboxylic acid product here, but that's an acidic enough compound that the strong base swirling around in solution will deprotonate it. So you end up with a carboxylate, which is why you then need to follow this up with an acid workup. So here is the mechanism for the saponification. So the hydroxide adds to the carbonyl carbon, breaking the pi bond, and then the carbonyl is reformed and the OCH3 is kicked off as the leaving group. And you have a carboxylic acid, which is acidic enough that it will get deprotonated by the strong base in solution, which is why you have to follow this up with an acid step. And esters can be hydrolyzed under acidic conditions. And this mechanism is what one would expect under acidic conditions and is simply the reverse of the Fischer esterification. So in this mechanism, since we're in acid, the first step is you protonate the carbonyl oxygen to make a souped up electrophile. Now water is your nucleophile. Then you do several proton transfers until you're ready to remove the OR group. So now we can collapse this intermediate to remove the leaving group, which is methanol in this case, and then a final proton transfer gets us to our carboxylic acid product. Esters can also form amides by reacting them with amines. And remember, you can go from something more reactive to something less reactive in one step easily. So an ester is more reactive than an amide, so you can form amides from esters. However, this process is slow, although it will occur. Therefore, most people, when they want to make an amide, will start from an acid chloride rather than an ester. We've seen previously that esters can be reduced to primary alcohols using lithium aluminum hydride. And this is a mechanism that you've seen previously. Essentially, hydride adds twice because you go through this aldehyde intermediate, which then gets attacked again by another hydride. So this is an animation of the hydride addition to an ester. So here the hydride adds to the carbonyl carbon, breaking the pi bond. The electrons go up onto oxygen. Now the carbonyl reforms and you kick off the O-ethyl. The ethoxide is the leaving group. Now we have a second hydride coming in, attacking the carbonyl carbon again. And we have an O- as the product. So we want to do a water workup, and that water workup will facilitate a proton transfer to the O-, giving you an alcohol product. If you use a special hydride reagent called DIBAH, which is diisobutyl aluminum hydride, shown here, it is much less reactive, so you can actually stop the reaction at the aldehyde stage and isolate the aldehyde rather than it going on to react to form the primary alcohol. But that is specific for this DIBAH reagent. We've seen previously that esters can react with Grignard reagents. The R group of the Grignard adds twice and you end up with a tertiary alcohol. Here's the mechanism which you've seen. So the R- of the Grignard does a nucleophilic attack. Here you're going to kick off OMe as the leaving group. You get to a ketone, which then gets attacked a second time by the R- of the Grignard. And then a final proton transfer gives you your tertiary alcohol. As discussed, amides can be made from any of the carboxylic acid derivatives that are more reactive than it, which are the ester, the chloride, and the anhydride. And the most popular way to make an amide is from the acid chloride. And you need two equivalents of whatever amine you're using because you get HCl as a byproduct and we want to neutralize that. Amides can be hydrolyzed, but this is a slow process and requires high temperatures. This is the mechanism in acidic conditions. So we're in acid, so the first thing you do is you protonate that carbonyl oxygen, then water is your nucleophile, it attacks the carbonyl. Then you have a series of proton transfers so that you are essentially converting the nitrogen group into a good leaving group. And then you're going to eventually lose that leaving group, which gets you to that intermediate, and then one more proton transfer gets you to your carboxylic acid. This can also be done with basic conditions. However, this is even slower than when acidic conditions are used. And this is the mechanism. So here hydroxide attacks the carbonyl. Then you lose the nitrogen group as a leaving group. And because we're in base, the carboxylic acid would get deprotonated because it's acidic enough to be deprotonated, and you would have to do another water workup or an acid step to protonate the carboxylate. Amides are reduced to the corresponding amine using lithium aluminum hydride. So this is a different mechanism from others we've seen. And notice here the carbonyl is completely removed, and we're adding two hydrides to that carbon. So here's an animation of the mechanism. So a hydride adds to the carbonyl carbon, and then the O- actually bonds to the aluminum, and that whole species, the O aluminum portion of the molecule, is going to leave as a leaving group. And you get this iminium looking intermediate, which then is attacked by a second hydride. So here's your second hydride. It attacks the carbon, breaking the pi bond, and now you have your amine product. So here is a big concept map showing how you can go from a carboxylic acid to an acid chloride. You can go from a carboxylic acid to an anhydride. You can go from a carboxylic acid to an ester. Notice you cannot go directly from a carboxylic acid to an amide. However, you can get to an amide from a chloride, an acid chloride, an acid anhydride, or an ester. So this is a big concept map, so take some time and look at this and see how all of these different carboxylic acid derivatives can be interconverted. And we'll finish up with a couple questions. So which of the following would not form propylbutanoate? So first you have to know what propylbutanoate is. So if this is a naming question, first of all, and then look at these 4 reactions and figure out which of those would not form propylbutanoate and why. Here for our question 2, we have a multi-step sequence. So see if you can follow each of these reactions and figure out what your final product would be. So you're going to react this with magnesium. I'll give you a hint. That's going to form a Grignard. And then what happens when you form a Grignard? When you react a Grignard with CO2, followed by acid workup, and then whatever that is, you react it with SOCl2, and then whatever that product is, you react it with excess methylamine. Put your answers in the chat. And that's it for carboxylic acid derivatives.